Hi everyone and welcome to my YouTube channel. My name is Muhammad Al-Hafi and I'm a Math Olympiad coach. So in this video, we'll be discussing and reviewing this year's IMO, which is IMO 2022, which was held in Norway. So in this video, we'll be particularly discussing the first problem of the IMO paper. So the IMO paper consists of 6 problems distributed on 2 days. The first day we have 3 problems and the time is 4 hours and a half. And the other day we've got also 3 problems and the same time. Okay, so if you guys are excited to see and discuss the problem 1 of the IMO this year, then let's get started. Okay, so it appears that this year's IMO, we've got the first problem is combinatorial problems. And of course, like usually when you see a lengthy problem, then usually it's a combinatorial problem. However, like don't be scared, because usually, in fact, when the problem statement is long, actually the problem isn't difficult. Of course, it's not a general rule. Okay, so let's actually start with the problem. Okay, so we've got the following statement. So the Bank of Oslo issues 2 types of coin. So we have 2 types of coin: aluminium denoted A and bronze denoted B. Of course, like when we'll be solving the problem, we'll just be focusing on A's and B's. Okay, Marian has N aluminium coins and N bronze coins. So we have 2 kinds of coins, and we've got like the same number of coins for each type. So we've got N A's and N B's. Okay, and they are arranged in a row in some arbitrary initial order. Okay, a chain is any subsequence of consecutive coins of the same type. So here they are defining like a term, which is a chain. What is a chain? So when we have, like, for example, many B's, for example, here, if we have like this is a chain, B, 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 4 B's next to each other, consecutive, and like this is another chain, A, A. Okay, so simply the term chain is any subsequence of consecutive coins of the same type, like A or B. Okay, then we're given a fixed positive integer k, which is of course less than or equal to 2n. Marian repeatedly performs the following operation. Okay, so now we have like an operation or an algorithm that's like it's applied each time, and it goes as following. She identifies the longest chain containing the kth coin. Okay, so like you can think of the number k as an index, because like it's between 1 and 2 times n. Of course, like we've got 2 times n coins here. Okay, so like we've got an index k, and this index, like we take a look at it, for example, in this, like here, if we've got k equals 4, then like this here, like k equals 4, like we're like focusing on this b, and like what is the longest chain here containing this b? It's this thing, like B, 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 this chain. Okay, so what do we do to this chain? Like from the left, of course, and moves all coins in that chain to the left of the row. So like we take these 4 B's and put them here, simply. Okay. And now we have an example. For example, like if n equals 4 and k equals 4, and we've got like the following initial order. So AA, B, 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 A, B, A. So you can see that here like n equals 4 because we've got 4 A's and 4 B's as well. Okay, and then they're like telling us that k equals 4. So let's like apply the algorithm each time. So first of all, like we start here, like A, B, 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 A, B, A. And what is the fourth, like we said that k equals 4. What is the fourth coin? It's this B. So simply, we will focus on this B. And what is the longest chain containing this B? Well, simply it's this, B, B, B. So we take it and move it to the leftmost. So like this. And now we have the following order. And now actually what is the fourth coin? It is this one, this A. And then like we apply the same thing, like this is the longest chain containing this A. We move it to the leftmost. We've got the following. Then this is the fourth coin. We do the same. And we have the following thing. And actually here you can see that now actually like it doesn't make any sense like to apply it anymore, because like we'll get just the same order, right? Take a look, B, 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 because it's the fourth. So like actually we're not moving anything to the left. so it stays still, and like it goes on from here. Okay. So now we understand like what is the operation, what is n and k, and now let's take a look at like what do we need to find or prove. Okay, so now actually we need to find all pairs nk with k between 1 and 2n, so like an index, such that for every initial ordering, so no matter like what order we have here, at some moment the leftmost n coins will be of the same type. So as you can see, like in this actual operation, for example here, like when n equals 4 and k equals 4, and for this particular thing, order actually, initial order, like here, the leftmost n coins, which are like the leftmost 4 coins, stayed the same. So actually they want us like to determine all the values or the pairs nk such that no matter what is the initial order, so actually we cannot choose a particular order. No matter what is the particular order, like we can always at some point reach like the state where like we've got n a's to the left or n b's to the left. Of course, the number of a's is n and the number of b's is n. So like we will have either n a's to the left or n b's to the left. Okay, so now actually let's like erase the problem statement because it's really lengthy, and then let's like discuss the problem and discuss the solution as well. Okay, so now let's discuss how to approach this problem. So first of all, like what is the technique that we'll be using here? So first of all, like we need to understand that we have two things like to do in this problem. So actually, like the pairs nk can be classified into two states. Either like this nk, either they are a solution or they are not. Okay, so what do we need to do in each case? So for like when nk is a solution, the pair nk is a solution, we need to prove that it works no matter what is the initial order. And usually like this is more difficult. So like here we need to prove that it works for all orders. And here like is actually the heavy part. However, here it's much easier. And why is that? Well, because here, when we need like to show that it's not a solution, it's enough just to bring one order, like one initial order, such that like the process will not actually terminate, like we will not have like n leftmost chain or n leftmost chain of a's or b's. So like here, simply just bring one example. Just one example is enough. One example to disprove. Simply. Alright. So actually, like this is much easier. This is much harder, usually. So let's actually now try to think about this problem. Okay, so now like we know what is the general algorithm of this solution. Now actually we need to try to figure out what is the solution, what is not the solution. Okay. So at this type of problems, like the first thing we need to do is actually to try to plug in some numbers. So basically like you can try, for example, n equals 1, 2, 3, 4, etc. Okay, so now actually let's try to take a look at a particular value for n and take a look at the possible values of k. Because first of all we need to choose n, then depending on n we choose k. So let's, for example, pick n equals 6. Okay, so let's like take an example, n equals 6. So let's take a look now, okay, at the case n equals 6. So now we have actually 6 a's and 6 b's, right? Okay, 6 a's and 6 b's. And we need to take some value for k. So actually let's, for example, start with k equals 1. Like the first, is the first coin a solution actually? Well, let's try to think of it. For example, let's bring some order. Something like that. Like we need to have 6 a's actually. Something like that. Okay, here we have 6 A's, 6 B's. Let's take a look at the first one, which is the first A. Okay, so if we apply it here and k equals 1, well, take a look. What is the longest chain containing A? This one. So actually it will not move, right? So actually from the beginning we are stuck here. So if we choose like the first coin, then from the beginning we're stuck. Like this will keep forever, keep on forever. So actually we've shown that 6-1 is not a solution, right? Exactly, so 6-1 is not a solution. However, actually you can, like, from the start think of the other cases for the other n's. Like when k equals 1, in fact any n will not work. So take a look for what happens if n equals 5? Well, the same. Like bring on this example, for example. Like if we have just A, and anything else like B here, then like it will stay still. These 3 A's will stay. Of course, like for n equals 4, for n equals even 2, like it will still be the same. However, when n equals 1, it is a solution, because when n equals 1, then we like just have AB or BA. So from the beginning, like you're done, right? Okay. So actually, if like in this case, just if n equals 1, it works. However, when k equals 1, like all the n's are refused except for n equals 1. Okay. What about k equals 2? Well, take a look. Like another, like it's similar to k equals 1, right? Because take a look, the same example work here. Like in fact, k equals 3 as well work in this case. Okay. So now actually, like we have a hint of like what is the solution here. So when k equals 1, like n should be 1, right? When k equals 2, n should be either 1 or 2, because when n equals 2, it also works. However, when n equals 3, then like we can apply the same thing, and so on actually. Like k equals 3, then you can see that in 1, 2, 3, and so on. All right. So what does that mean? What does that mean? Actually, like now we need to do two things. First of all, like understand like what is happening here, what is the pattern, and second of all, like formalize our proof here. So first of all, let's take a look. What does that mean? So when k equals 3, then n should be 1, 2, 3, right? So that means that n must be less than or equal to k, right? So k must be greater than or equal to n. Like that, what actually like this thing means. So simply, that means that k is greater than or equal to n. Like this is basically our first claim. So our first claim is that if k is less than n, then we will not have a solution. So we need actually to disprove all the cases when k is less than, exactly less than n, right? And that can be done easily. Well, of course, like we will not take this arbitrary order. We can just bring any particular order, right? And like what is the best order like to bring here? Like let's not just take 3 A's. Let's take all the A's first of all. And then like let's do it as the following. Let's take A, like all our A's. However, of course, we don't want to take all our n A's, because this will be a solution, right? So we will just keep 1 A not here. So these are total of n minus 1 A. Then we will take 1 B, and then the other A, and then like all the other B's. So simply here we have n minus 1 B's as well. So actually, like you can see that this immediately solves this issue. Like this example, for any n, this shows that k must be greater than or equal to n. Because if k was less than n, then it's like one number between 1 and n minus 1. So one number between 1 and minus 1, that means this chain will like stay still. It will not move. And that simply means that like we don't have n A's or n B's on the leftmost. Alright, so actually now our first claim is done. We've proven our first claim that k is greater than or equal to n. Of course, we know that k is between 1 and 2 times n. So now actually like we're halfway, because like we eliminated basically nearly half of the the cases. So now we know that k is between n and 2 times n. Okay, that's actually awesome. Alright, so now we've shown that k must be greater than or equal to n. So let's write that down. So k must be greater than or equal to n. But like, are all the numbers like n, n plus 1, n plus 2, up to 2 times n, like satisfy our problem? Well, actually, it turns out that they do not. Not all of them work. So we still need to exclude other cases as well. Okay, so let's stick to our example, n equals 6. And now actually the easiest part is not to discuss from the left, let's discuss them from the right. Because like we've already excluded the first n coins, so now we expect the problem like to be from the rightmost, right? Okay, so let's now actually take another example to see why they not all satisfy our problem. So let's take like a simple example, which is like A, B, 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 A. Okay, and 3 B's. So 3 A's, 3 B's, 3 A's, 3 B's. Now actually, if n equals 12, k equals 12, you can see that actually that this immediately like does not work, because take a look here, this B, like let's move it to the left, then we have these 3 A's, we move them to the left, then we have these 3 B's, we move them to the left, and so on. Actually the process like never ends, so we never have n or which means like here in this case 6 coins of the same type at the leftmost. Okay, so actually k equals 12 doesn't work. And of course, like it's not just 12 doesn't work, in fact 11 doesn't work, 10 doesn't work, right? Because we can do the same thing here. So in fact now let's just discuss the even ends, because discussing the odd ends like is similar, and like it's a bit boring like to discuss these two cases. Like you need to be accurate actually to use the floor function or like some other things as well. Okay, so now let's just discuss the even ends at this case, and then like we will discuss the odd cases as well at the end. Okay, so basically, of course, not just for n equals 6, like we can do the same for n equals 4. We can bring this example for n equals 4, A, B, B, A, B, B. And here like, if k equals 8 doesn't work and k equals 7 doesn't work. Okay, so actually now, like a general thing we've done is that we've shown that k must be less than or equal to, like what exactly? Well, actually, here we have n over 2, n over 2, n over 2. That means 3n over 2, right? So here, like in this case, let's plug in 6 here. So 6 over 2 is 3, 3 times 3 is 9. So in fact, 1, 2, 3, 4, 5, 6, 7, 8, 9. Exactly. Like here, if you put 4, like you will get 6. 1, 2, 3, 4, 5, 6. Exactly. So actually now we're complete. Now we've shown that k is greater than n, greater than or equal to n, and less than or equal to 3n over 2. Well, actually, it turns out for the odd ends, like you just need to put here plus 1. Like I will leave this thing to you. It's really simple. Like why here we have 3n plus 1 over 2. So it still works for the even ends, and for the odd ends it works, of course. So like you can use the floor function if you want. You actually can even discuss the two cases separately, like odd ends and even ends. It's not a big deal really. Okay, so now actually, like we've done the easy part of the problem. It's not that easy actually. Like it's like I do think that it's even half of the marks like are for these two cases. Maybe like here 1 mark, here maybe 1 mark, or even like more, because this is a bit more difficult than bringing an example here. So maybe like these 2 points and here 1 point. But however, like now the most difficult part is here at this case, when k is indeed between n and 3n plus 1 over 2. Because as we mentioned in the beginning of the problem, now we need to show that it works no matter like for any arbitrary order, initial order, right? So now actually let's try to show that. Alright, so now actually we just need to show that these numbers, like these pairs, nk, when k is between n and 3n plus 1 over 2 do satisfy our problem. So actually, let's take a look. Let's assume that they do not satisfy our problem. Let's like take a pair in K such that K satisfies this inequality, and let's assume that it does not satisfy our problem. So what does that mean? Well, that's simple. That means that like we will keep applying our process forever without having n leftmost chain, basically, like of A's or B's. So you'll keep doing it again for infinitely many times. And here actually, like when we do apply this process, like at this type of problem, when we have an infinite number of times you're applying something, and we need to show that in fact it terminates at some point, there is a very important and nice technique to solve such kind of problems, and this is called basically a monovariant. So basically we need to find a monovariant. So what is a monovariant? Well, a monovariant is really like something like it's changing. However, it's changing in particular like it's either ascending or descending. For example, like let's say we have something that, for example, starts with 5, then it just decreases. Like it can never increases. Like it goes to 4, then to 2, then to 1, and then, for example, to 0. So this is a monovariant because it's like just going as descending, or maybe it's descending. Here it's descending. Maybe it's just ascending. So 5, 7, 8, and so on. So we can never have like 6 here, for example, or like here, like you have 3. It's just descending. And in fact, like why is this really nice and like it solves our problem? This like a monovariant. Well, it's simple. Like the idea is simple. Like try to spot a monovariant that is decreasing, a decreasing monovariant, and that must stay like positive. So what does that mean? Like let's assume that the process goes infinitely many times. Okay, and let's like assume that we have some monovariant x, let's say. So we start our process when x, let's say, is, for example, some number m, some positive number m, and this monovariant, like this x, actually should be a positive. Like it should be actually bounded. So, for example, greater than or equal to 0. And if we show that this x is monovariant and it's in fact decreasing, like it should be decreasing, not just like not increasing. So like we cannot just have 5, 5, 5, 5, because we can go like infinitely many times just with 5s, right? However, if we show that it's still like it's decreasing, like every now and then it must decrease, that means that after some time, like we will have like n minus 1, n minus 2, and until we reach 0. However, when we reach 0, we cannot go any further, right? Because like we know that x must be greater than or equal to 0. So that contradicts the fact that we're going infinitely many times. Because if we're going infinitely many times, that means we need to go to the negative. However, we know that x is positive. So that basically like ends the problem at once. If we can spot a monovariant and show that it's greater than or equal to 0 and it's decreasing every now and then we are done with this problem. Okay, so let's actually try to find what is this monovariant. Actually, it's not that difficult to bring this monovariant as you might think. Let's just like try to analyze some position, and it will come naturally. So let's take some example. Okay. So now actually, like let's assume here we have the 2 times n coins, and here we have the first n minus 1 coin, and here like we have our interval, and here we have the other, if you remember, like there, floor n over 2 coins. Okay, and here here are the set of coins that we want to show that they work, like this interval. Like it starts with n and here, like it ends here. Okay, so let's actually take a look here. So let's say k is here. What are we doing in our problem? Basically, we're taking the longest chain that contains k. Let's say like it's right here. Like we'll take it and move it to the leftmost here. Let's assume here like we've got many a's. A, 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 A. Let's say we're focusing on this K. Of course, here what should we have? B, right? And here what we should have is a B, right? And it's like something we don't care here. Okay, so what is happening? Let's take a look. We're taking these A's and moving them to the left. However, what happens here? Take a look. This B and this B, they get combined, right? Exactly. So like here we must have a B, here we must have a B, and they will get combined. What does that mean? Well, here you can spot the monovariant simply, and it's really nice and clear. The monovariant is simply the number of chains. That's it, the number of chains. Remember, a chain is a subsequence of coins of the same type. Well, like now let's assume we have, for example, 10 chains, 10 B chains. Now when we apply this, then this chain, this B chain, and this B chain, they will get combined. That means that now we have actually 9 chains. And in fact, when we apply it again, then the number of chains in total will decrease. And actually this is a monovariant because it is greater than 0, of course, and it's it must decrease, right? At each step, in fact, it will decrease. So that in fact ends our problem at once. However, are we done? Well, actually we're not done yet. Be careful. Why? Well, it's logical here, anything here, we will always have a chain here, and we'll move it to the left. And of course, we need to pay attention. Do we have necessarily a B on the left and B to the right? Well, of course we have a B to the left. Why? Because take a look here, we have n minus 1 coin, and here we have the n coin. So of course we have on the leftmost, we must have a B here, because they cannot all be A's, because here we have n minus 1 and here n. Okay, so we must have on the left a B. In fact, maybe we just need to discuss the case where we have initially n A's and then n B's. And of course, we don't even need to discuss that because it works, of course. However, take a look at the right. Here, do we necessarily have a B? Well, actually not. We might just have A's up to here, right? Okay, so we need to discuss that. So we need to discuss the case when we have all A's here. However, that's really not difficult. Don't think it's difficult, because that means we have already here floor n over 2 A's and even more. So that means that this chain, the length of this chain, let's say the length of this chain let's say 1, the length of this chain is, that means it must be greater than or equal to floor of n over 2 plus 1, right? Because we must have an A, for example, here, and here all of these are A's. Okay, no problem. Let's apply the process. These A's will be moved to the left and will be replaced with another, right? Now actually all what we need to show is that this monovariant, it decreases just once, because we have infinitely many times, if it does not decrease, so at some point it will stay constant, because it cannot increase for sure. It either stays constant or decreases. So let's assume that at some point it will stay constant. We just need to prove for sure that it will decrease at some point. So here it did not decrease, no problem. However, now when we move them here, now we will have, if we have here A's, then we will have B's here. And we can do the same thing. We must have the length of the other chain, the B chain, it must be greater than or equal to floor of n over 2 plus 1. And guess what? We will apply the same thing. We move it to the left. And we must have the same thing for A's again. That means that the length of chain 3 must be greater than floor of n over 2 plus 1. And now wait a second. Can that work? Can we have the length of the first chain, the A chains, greater than this, and the another A chain, it's also greater than that? Well, let's just sum these two inequalities. That means that the length of the A chain, in total, is greater than floor of n over 2 plus floor of n over 2 plus 2. And that's in fact greater than n. So that means that the length of the A chains is greater than n, or sorry, that means that basically the number of A coins is greater than n, which is a contradiction. So guess what? Now actually for sure we must have that our monovariant, the number of chains must decrease, from like time to time. That means that basically the process cannot go like infinitely many times, and that means it must terminate at some point, and that means that in fact we've now shown that k, any k between n and 3n plus 1 over 2, like it works indeed. So let's now summarize what we've done with this problem. So first of all, we've read the problem statement, we understood like what should we do in here, like we have two cases, either a solution or not a solution. In a solution we need to show that it works no matter what, or initial order. On the other hand, when it's not a solution, then just one example, that's like is enough. And like we tried to mess with like some cases. We, for example, took n equals 6 and tried k equals 1, k equals 2, and we immediately figured out that it's not a solution. We immediately figured out the inequality in fact, which is k is greater than or equal to n. We immediately proven that, and that's already like maybe the first point we get. And then we in fact discovered that like by going from the rightmost, that for example k equals 12 and n equals 6 also is not a solution, because we were able to bring a simple example to disprove that. And in fact we showed that k must be less than or equal to 3n plus 1 over 2. As I mentioned, you can discuss the odd cases and the even cases like separately, or you can combine them at once like in this inequality. So first of all we show that k is greater than n, then k is less than or equal to 3n plus 1 over 2, and then like the hard part came, in which like we identified something, like we spotted something that's called monovariant. We explored like what is this monovariant, and it was basically the number of chains. It was really like nice and clear, because like it was like basically telling us that come on, I'm the monovariant that you need. Because like when we took the A's here and moved them to the left, then we immediately like the B's here and the B's here combined together, meaning that the number of chains was decreased by 1. And like we needed to discuss a particular case, like if the rightmost, we have just A's to the rightmost, so we basically with 3 inequalities we killed the problem, and we immediately brought our monovariants in order to show that the process must terminate. And that basically finished the problem. So we've got 3 parts of this problem. The first one is this inequality, the second one is this inequality, and the third part, and the most difficult, is to show that any k with these inequalities satisfy our problem. Alright, so now we're done with the first problem 1 of this IMO. And in the next video we'll be like probably discuss the problem 2 of the IMO, and we'll see like is it the same difficulty or it's difficult. So I want you guys to tell me in the comments like what did you think of this problem? Is it difficult or is it easy? Is it medium? Please tell me in the comments. And if you have like additional notes, or like you have a solution that's different from our solution, then please just tell me what is it in the comments. If you have any question, just tell me in the comments. And please guys, like the video, share and subscribe to the channel, and see you guys in the next video.